Now in R2, it's very easy to do a geometric depiction. So, you know, if this is our V1, this is our V2, well, here could be your V1. And that's the eigenvector that corresponds to lambda equals 6. This eigenvector corresponds to lambda equals -6, and it's going to be 1, -6. It'll be this vector in white here. We then ask, okay, well, let's see, what would happen if we map the unit circle? What do you think we might get? Well, here's a circle, presumably radius 1. We take a vector from the origin out to the circle in the direction of V1. In other words, we go along V1 till we get to the circle, and there's a little vector. Okay? If we apply our matrix to that vector, we get a matrix that's 6 times as long in the same direction as the eigenvector. Okay? And if we do that to a vector from the origin out to the circle along the V2 vector, well, that vector is going to be parallel to V2. When it's mapped, it'll map to -6 times itself. So this vector maps up to this one. This vector maps to a vector in the same direction. This vector maps to direction in the opposite direction because it's got a negative eigenvalue. Okay? And similarly, if we do a vector from here to here, it'll map to a vector down here. If we do a vector from here, the center of the circle, out along the line of the V2 vector, but in the opposite direction, it'll map to this vector. Now, another thing we can say is that I said this is a basis of R2. What does that mean? It means I can take any vector in R2. So I just drew one here. That's V. Okay. There's our vector. I can express that vector as a multiple of V1 plus a multiple of V2. Geometrically, that means I could go along the V2 vector until I get to a point, go along the line of the V2 vector until I get to a point where moving from that point to the tip of the V vector is going to be in the direction of the V1 vector. And I labeled these wrong. This should be V2. This would be our C2 V2. And this would be a C1 V1, a multiple of V1, because this is in the direction of V1. Okay? So, this is a C2 V2. This is a C1 V1, parallel to V1, different length. So V equals C1 V1 plus C2 V2. Okay? Now, several things we can say about this. The representation of this vector V relative to the basis B, and let B be this eigenvector basis. Okay? The representation of our vector V with respect to B is going to be C1, C2, whatever the C1 is that we need for this vector, and whatever C2 we need for this vector. Okay? That's our representation of this vector. It's a perfectly valid representation of the vector. It tells us how far to go along V1, how far to go along V2 to get V. Let's just say that in the standard basis, remember this is 6 units, so I'm saying it's maybe about 10 units out to here and maybe 5 units up to here to get from the tail of this vector to the head. So that vector, according to a standard basis, would be 10, 5. Okay? Now, if it's 10, 5 according to the standard basis, what are C1 and C2? What's its representation according to the eigenvector basis? Well, we can figure that out. Okay? Now I wrote this. I'm just going to kind of erase that because I ended up not using it. kind of ignore the VS and VB for a minute also because they're already written up here, and I'm not sure why I wrote them there. But to say that C1 V1 plus C2 V2 is equal to 10 5, which we would have to do, okay? Well, that equation is easily written as C1 times 1 6 plus C2 times 1 negative 6 equals 10 5. If we can find the C1 and C2 to multiply by 1 6, this vector, and by 1 negative 6, this vector, to get 10 5, then I have my C1, C2 representation of the vector with respect to the eigenvector basis. Well, this translates into this matrix equation, okay? Very straightforward. And you notice that in this matrix, this eigenvector is in this column, and this one is in this column. So we just have a column of eigenvectors matrix. If we multiply that by the C1, C2, we're going to get 10 5. So to solve, we solve the equation by multiplying 10 5 by the inverse of this matrix. So here's our solution. C1, C2 is the column of eigenvectors matrix inverse, the inverse of that column of eigenvectors matrix multiplied by 10 5. We've already seen this. We've already done this last week or maybe even late the week before. Things got smudged here a bit, but our representation VB is going to be our C1, C2. So this is our VB. And it's equal to P inverse V sub S, where P is the eigenvector matrix. And this will be true for any set of eigenvectors that form a basis. Okay? You just put the eigenvectors in the column because you're going to get an equation just like this, but you use the two eigenvectors, whatever they are, for any other space, and it works out. So